All right, so our next speaker is Zaran Liu from MIT.
Okay, hi everyone, my name is Zhaoran Liu and I'm a postdoc at MIT. Today I'm excited to tell you about our recent work on literal dots and why we believe Roman is a key facility to answer some of the most debated questions for this mysterious population. Okay, as Dale and Steve introduced yesterday, literal dots is a population that has been discovered in the GWT at the early stage that has been showing a red and optical compact morphology and also a broad Barmer line with H alpha above like 2000 kilometers per second. So this is a characteristic feature of the supermassive black hole where the gas orbiting the supermassive black hole makes this broad feature. However, if we put some standard agent tests on the literal dots, we found they are actually few on those agent tests that we threw them. First of all, the literal dots are extremely X-ray faint, so they are 10 to 100 times fainter compared to the type 1 region. And also, the mid-infrared observation and the sub-millimeter observation has been showing that the LRDs has host little hot or those cold dust populations. And LRDs is also very abundant. They are more than 10 to 100 times abundant compared to the quasi-luminosity at redshift around 5. So, while the LRD looks like the massive black hole at the first glimpse, but they must have some properties that is very different from the supermassive black hole that we are familiar with. And here comes the basic properties of the LRD. If you take the broad line width as a face value and apply the standard Variability calibration to calculate its black hole mass, this is what you get. So the host stellar mass that is measured from the clustering analysis suggesting that the LRD host is having a stellar mass of 10 to the 7 to 10 to the 8 solar masses. Well, the Variability black hole mass estimation is also giving you a 10 to the 7 to 10 to the 8 solar masses black hole. So taking as the face value, this is suggesting that there is a black hole to star ratio that is more than 2 to 3 times higher compared to the local calibration. And if this is true, this means we need to rewrite our understanding of the black hole seeding and the growth theory at the early universe. However, this is the uncomfortable part, is that we might not actually knowing the black hole masses of the LRD. Well, the Variability calibration is giving you 10 to the 7 to 10 to the 8 supermassive black hole, but there is growing evidence that the LRD may not look like that, and it might instead look like this, where a massive black hole, or maybe not massive black hole, where a black hole is wrapped in a very dense envelope, and the broad H alpha is emerging from the scattering when the H alpha is traveling from its way out this envelope. So in this scenario, if you do not touch the broad line itself, and if you apply the escape velocity or the Eddington limit argument, you will actually get a black hole mass of 10 to the 5 solar masses. So this is a simple population, but there is 2 to 3 times difference on the most basic properties of the most abundant agent population that we have found in the GWT. And this suggests that we need some independent proof that don't rely on the interpretation of line or SED at all. And variability is such a probe. So in every massive black hole that we have ever monitored, we saw them flickering. The massive black hole is flickering slower and shallower, while the small black hole is flickering harder and quicker. And like light curve itself with the black hole with a calibration-free method. So here you can show this is a light curve of for black hole that is ranging from 10 to the 5 to 10 to the 8 solar masses. And by measuring the variability of the black hole, you can get an estimate of its black hole masses. And the characteristic timescale of such black hole is ranging from weeks to months in the red frame. And yes, this gives us a very clear prediction is that if the LRD is actually the accretion agent that we are familiar with, we must be able to see the twinkle. So we test this scenario. So this is our cycle 4 GWT program called Twinkle, and the PI are these 3 great people. So the idea of the Twinkle is to monitor some of the very first discovered LRD back to the cycle 1 observations, and which enable the longest baseline enabled by the GBST observations. And the key is we are using the near-camp slitted spectroscopy. So the feature of the near-camp slitted spectroscopy is that you get all spectra at once within its field of view within one single explorer. And you also get both H-alpha profile and the continuum within the same shot. So there is no slits, there is no target selection, and there is no slit loss correction. And this is the spirit of this program. We took 5 epochs over 3 years, and this enables us to trace the variability of LRD in week, 2 months to half a year baseline. And this is what we get. So in the left, we are showing the H-alpha light profile of the LRD epoch by epoch. As you can see, we do not observe any significant variability as suggested by the light profile. And in the right panel, we are showing you the continuum from 9 selected LRD. And for every epoch, we only observe a few % difference compared to the first epoch, which is actually within the measurement uncertainty. So we observed 27 broad H-alpha emitter at redshift 427 for their photometry and also Grism spectroscopy, and we observed 0 of them is showing any detectable variability. And if you compare this with the simulation that is drawn from the real SDSS light curve from the local universe where most of the variable calibration is based on, you would expect there will be certain sources showing detectable variability if they are indeed act like the SDSS AGM. But in fact, we observed 0. So this is more than 6 sigma deficit from the SDSS expectation. And this known variability is hold for both LRD and non-LRD and hold for both H-alpha and continuum light curve. So our observation suggests that if the whatever it sits inside the LRD, it is not like a textbook like a accretion disk that we know. And now let's zoom out to the whole population, because the demographic itself also carries the important physics, such as the number density. The number density tells us about the whole scale, the duty circle, and the lifetime of this population. And so we already know the rise. So from the multiple independent selection, we have been seeing that the LRD number density is rise and peaks at redshift around 5, which tracks the newly formed halo of 10 to the 10.5 and 10 to the 11.5 solar masses. However, below the redshift 2, where it's actually the different model diverse, there is no measurement at this moment. So this would be the discovered space for the Roman, and this is not a question for GBST anymore. So here we are showing the Roman high latitude wide area survey. The high latitude wide area survey will cover more than 2,400 square degree, and which enable us to capture the H-alpha at 0.5 to 2 in the Grism spectroscopy. So this is exactly the redshift where the GBST is missing, and this is exactly the redshift where the different model is getting to diverge. And this arrow is showing you the expectation from the different model. If the LRD has a number density that is similar to the redshift around 2 number density that is being reported by the Eiger, then we would expect a few 100,000 LRD would be detected in the high latitude wide area survey. But instead, if the LRD is directly dialed to the floor, that is constrained by the local survey such as SDS and the DESI, then we will only be able to detect a few hundred. So in either detection, as this big difference would be decisive. Okay. The Roman will not only enable us to count the LRD, but it will also enable us to time the LRD. The high latitude wide areas time domain survey will cover the Grism spectroscopy in over 5 square degree in every 5 days for 2 years. And this is a rest frame of 1 year at redshift 1. And for comparison, Twinkle is probing the rest frame baseline of half a year at best. So this will enable us to do direct cuckoo tests and black hole mass constraint in a population level. And it's very important measurement to independently constrain the black hole masses of this population. And we already know that this search won't come for empty. So here is our ongoing work where we search the interior GWST Grism archive to search for the broad HRI emitter. And we already found hundreds of the LRD has been discovered at redshift 227 in this interior Grism archive. And there is already many redshift 223 LRD being discovered. So we know that this population has survived to the edge of the Roman window. And what we need is just to observe them. Okay, so here is my summary. We know that LRD is a new class of astronomical physical objects that has been discovered by GWST, and they are abundant at high redshift. And we monitor 27 LRD in a rest frame baseline of half a year, and we observed 0 of them is showing a detectable variability. We suggested that the standard virial calibration is not applicable to this population. And Roman is very essential for our understanding to the littoral dots. The high latitude wide area survey, we're going to count them at the loaded censuses, and the high latitude time domain survey, we're going to time them. Thank you.
Questions? Yeah, Dan.
Thank you. Nice talk. I'm fascinated by the lack of variability in the non-LRD broadline sources. So those sources have black hole to solid mass ratios that agree much better with the local AGN, and they don't show any signs of a black hole star photosphere that's causing scattering, and yet they're still not showing any variability. So I'm curious what your interpretation there is for those sources, because they look more like regular AGN, but they're also not varying. So do you guys have thoughts on what might be happening there?
Yes, one possibility that has been proposed by Wendy earlier this year is that for the blue AGN that you are seeing here, it's just a different mixture of the black hole star and if you believe this picture, the black hole star and the host galaxies. So if you put a higher host galaxy fraction into the black hole star templates, then you will get an SCD that is very similar to the broad blue AGN that you are seeing here. But indeed, the engine is still a black hole star that is in a dense galaxy. Yeah.
Thanks.
Could you go back to the slide that shows the actual data of the bingo?
Yeah.
I totally agree with you, by the way, that the broad line width only gives you an upper limit to the possible black hole mass, and I really want this to work. I really want your project to be successful. I want to believe you that there's no variability here. If you look at old work that was done on this decades ago, me and other people, the amplitude of the broad line variability is not all that large, typically 15–20%, and you're looking at more like CFOT 1.8, CFOT 1.9. So you're looking for a pretty small change.
Yes.
And so the real question here is, if you compare to the Sloan result, which does have the change there, do you have the same signal-to-noise ratio as the very nice Sloan spectra, so that you can really say you did not see the variability that they did see?
Yes, actually for each spectra, we obtain a signal-to-noise ratio floor that is constrained from the live free window, and we apply the exactly same signal-noise floor when we simulated from the Sloan spectrum. So, thank you.
Any other questions? Oh, yes.
Hello, this is amazing result. So I remember there are some other studies for some maybe other populations of low redshift little dots showing they claim that there are some variability similar to the general AGN population. Although I don't know what do you think about it? Will they be a different population, or is there any difference between your methods? Do you have any comments?
Yes, actually there is some recent work that is using the DESI and the DESI LRD by Lin and by Park et al. And I think this study dozens of the LRD, local analog of the LRD, and they do not detect variability except for one, the so-called G1717. But in that case, they detected variability only in the Ys, but not in the optical light curve, which is also kind of weird, and it's not the similar thing that we would expect from the type 2 agent.
All right, let's thank the speaker one more time.